Hello everyone. Good morning, good afternoon, whatever, whenever you are watching this video. Uh, let's begin with more of probability. We've already seen what are the some of the definitions. And we also seen what's the classical definition of probability is. Today we would see certain things in classical probability and also when it is limited. Use is limited. Okay. So first of all, let's look at this one, which we have seen already. It's called as mathematical probability, experimental probability, or also called as priori probability, and so on. What does it mean? If you look at the definition of classical probability, it's like the number of events favorable, number of outcome favorable to an event upon total number of outcomes, right? That's a classical definition of probability of a random experiment, right? For example, if I toss a unbiased coin, okay, then probability of getting head, I have at least one outcome which is favorable to this event, right? And of course, it's exactly the probability is 1/2. Okay, so there's equal chances of getting a head and there's equal chance of getting a tail, right? So they are equally likely events, right? Getting a head and getting a tail is equally likely because the equal number of chances of getting a head as well as the equal number of chance of getting a tail. So similarly, if I draw a card from a pack of well shuffled cards, okay, if that is my a random experiment, then getting an ace out of this would be total number of outcome getting. See, getting an ace, right? Picking an ace, the total number of outcome would be. I mean, what's the probability that I would pick a ace first of all, right? Card which is an ace, right? It would be 4 by 52, right? So there are four aces. So picking a ace can be, I can pick any of the four aces, right? So it would be 1/30. So picking each ace, the probability is 1/30. It's equal. That's the idea. So if I look at the definition of classical probability, you look at that, you kind of understand that you are not doing an experiment in order to decide your outcome, right? If I tell you that if I toss a coin, what are the possible probability that I would get a tail? You're not kind of carrying out the experiment. Rather, you just use your logical thinking to get the outcome, right? So here, this in this probability, you don't require any kind of statistical or experimental data, right? You just need logical thinking, right? That's called as mathematical probability because you are not doing any experiment, right? But neither you are taking any previous statistics. We don't require previous statistics here. What happened prior to this, right? It's not necessary for us for deciding what would be the probability of an event, right? So what we do here, it enables us to calculate the probability of an event just by logical reasoning. Before we just make and check whether the whatever things we have said is correct or not, right? So because of that, we also kind of term the probability as priori probability, right? So that's another name to priori. I mean, the classical probability is also called as priori probability, also called as theoretical probability or mathematical probability, and so on. So I hope that thing is clear, right? So whatever we have seen so far, if I look at this one, there would be certain shortcomings because if I look at the formula of the probability definition, we have said that it is number of outcomes upon number of outcomes favorable to an event. What do you mean by a number of outcomes favorable to an event? Is it's in favor of that event, right? Uh, so if I look at my random experiment as tossing a die, and if I look at the event as getting a number bigger than 2, then how many events are favoring that? Right, those would be favorable to that. Getting a number 2 greater than 2 would be either I can get 3, 4, 5, or 6. So there are 4 outcomes which are favorable to that kind of event, right? So what happens is, first of all, I should know that you cannot have, first of all, you cannot have infinitely many number of exhaustive outcomes, right? Your number of outcomes should be finite, right? You cannot have, for a random experiment, I should have my outcomes to be finite. In order to apply the probability, the number of outcomes, right? Exhaustive outcomes, and if you collect all the outcomes, you get a so that has to be finite. You cannot have infinite amount. Okay, that's a very first con of I would say this is a very first con, rather, the very first con of applying classical probability theory is this is a con that my n should be finite. The number of outcomes should be finite. Okay. Second one is I should know the exact value of n. I cannot make I cannot start without knowing what is the actual value of n, what is the total number of n's I have, right? First of all, outcomes cannot be infinite, right? You cannot have, for a random experiment, you should not have infinite many outcomes, because I'm finding a ratio. If I'm not able to know what is n, right? Then I'm in trouble, right? I hope n is in. I can use small n, so I don't know if you have used small n, you can check the previous argument. This n has to be finite. If this n is infinite, then there's a problem. Okay, this guy has to be, first of all, it has to be finite. You cannot have infinitely many n's, total number of outcomes of the if an event, and you should know all the outcomes, right? For example, if we have a jar, right? And we have a some balls inside that, say black and white balls. Okay, and I don't know exactly how many white balls and how many what exactly is the number of them. Then I don't know what's the probability what is the probability of choosing a black ball or picking a black ball. So I need to know, if I want to find a probability, I need to know certain things about how many black balls, how many red balls are there. I can't just say that there are black and white balls in this jar, right? Tell me what is the probability that I would pick a black ball. These kind of situations are not dealt in classical probability. You should know exactly how many total outcomes you can have. Okay, that's one thing. The third con for this type of probability is you should know that your outcomes are equally likely. That means there is equal chance of occurrence for all outcomes, right? For example, tossing a coin, there's equal chance of getting a tail and getting a head. Similarly, if I look at throwing a die, there's equal chance of getting one, there's equal chance of getting two, equal chance of getting three, equal chance of getting four, equal chance of getting five, and equal chance of getting six. So your experiment or the outcomes has to be equally likely, right? For example, if I have a situation that I want to find out if a person jumps from a topmost floor. Say if a person jumps from top of Burj Khalifa, right? A person just tries to jump from the top of Burj Khalifa. Then if I want to find out the probability of his survival, right? Uh, it won't be equally likely. See, uh, 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 survival and that are not equally likely events, right? They are not. There's not exactly equal number of chances. There's no equal number of chances, right? Because if he jumps from Burj Khalifa, it's very high probability that he's gonna die, right? The chances of survival is pretty minute, pretty negligible, right? So this is not an equally likely outcome. That's not equally likely outcome. I hope you know what is an equally likely outcome. What do you mean by equally likely outcomes? They have the same kind of chances of occurrence, right? So jumping from a top of a building is not a equally likely event. So um, I can't apply probability theory to this. So there is there are limitations for this kind of probability theory, but these limitations are taken care by another way of defining the probability. It is called as empirical or statistical probability, right? Let's look at that. What do you mean by empirical or statistical probability? So let's look at statistical or empirical. So this kind of helps us when classical theory of probability fails, right? When there's a problem in classical probability theory, we use something called as statistical or empirical probability. Okay, let's look at this one. What does it mean? If an event, or if an experiment rather, pardon, if an experiment, okay, is repeated n times, and if m of these occasions, m of these occasions, an event an event A is observed to have occurred to have occurred, then the probability of event A is given by is given by probability of A is the ratio of m over n as n becomes sufficiently large or larger and larger. That is, probability of A, right, is nothing but limit of n going to infinity of this thing means n is taking any value, any large value, right? This is not possible when we do uh, classical theory of probability, because my n has to be the total number of outcomes has to be. So why is this? Okay, so let's write down remark, write down some note. Why is empirical, or why would we use statistical probability? Well, uh, do this. This approach of or definition is used only when definition is used only when the outcomes are the number of outcomes are not known, or not known to be equally likely. Okay, when the number of outcomes are not known to be equally likely, are not known to be equally likely, not known to be equally likely, uh, and it is possible to conduct the experiment a reasonably large number of times subject to the budget and the cost, right? Within the budget, in the budget, right? That is within the budgeted, we can say, time and cost. Okay, right? So what happens in empirical probability is you can carry out the experiment however large number of times as possible. Okay, right? Uh, all allowed in statistical or empirical. If I look at statistical probability or empirical probability, it's an experiment performed repeatedly under essentially homogeneous and identical conditions, right? Then the limiting value of the ratio of the numbers of times the event occurs to the number of trials, as the number of trials becomes indefinitely large, right, is called the probability of happening of the event. Okay, and it's being assumed that the limit is finite. So it's assumed that it's finite, and so that's what we write. That's the definition of statistical or empirical. For example, let's look at some examples of the situations where I can use this. Right? So if I look at this example here, that a coin is thrown 200 times, okay, then what is the probability that head will occur 75 out of those 200 times? Okay, look, if I look at classical theory of probability, then it tells me that uh, if I throw a coin, whatever the coin is, uh, then the chances of getting hit has to be half, exactly half, right, or the 50% chance, right? But if I kind of repeat this experiment, um, say n number of times, it's not necessary that every time the probability of getting hit would be half, because there would be instances that I don't get hit at all, right? So in this case, in this kind of problem, say the probability, that is classical definition of probability, it doesn't come to our aid, right? Similarly, if I look at rolling a dice, right, then say 100 times I'm rolling a die, then what's the probability of getting the probability of getting say hey 25 number of times, right? So what happens is, in this case, we got to do certain experiment in order to get a exact, or we need to find a statistics kind of to get the exact probability, right? So in this case, what we do is we calculate, right? We kind of calculate the probability by counting, right? Take the statistics, count the number of times that the event can occur in a certain number of trials, right? So that's what we do in statistical or empirical probability, right? So what does the empirical probability do is, it kinds of provides a validity to the classical theory of probability, right? Uh, you know, so for example, if the same example, if taken, if I take a unbiased coin, right, and if I toss it at random, right, say uh, just one time, say suppose, then the probability of getting hit is exactly half, right? But if the same coin, if I toss it 20 times, then classical probability would tell me that you should get 50% chance, right, of getting hit. That means I should get 10 hits, right? But that's not true, because if I look at in general the real problem, if I toss it 20 times, it's not necessary that I should get even 10 hits, right? I can get all tails or something like that, right? So that's not always 50% of, or 50 or equally likely outcomes in real life is not possible, right? So it's just theoretical thing, right? Equally likely outcomes are not really possible in real life, right? So thus empirical probability approaches the classical probability as the number of trials becomes larger and larger, wherein the general classical definition of probability fails, right? that's where the empirical probability takes in charge. Okay, but the probability of this type is also having uh, certain kind of limitations. For example, when we say n goes to infinity, that means we are carrying out however large outcomes we can, but that's not always really possible to take care of outcomes however number of times. So in fact this n is finite in empirical property also, but it can take any large value. You don't know what exactly would be the infinite number of times you are allowed to repeat the experiment, but it can be possible to kind of repeat the experiment any large number of times. There's no restriction on the number of outcomes or the number of times you should repeat the experiment, right? So that's possible, right? uh, that's one thing. So let's write some limitations of this kind of probability also. There are, if there's a probability, there should be some kind of limitations to that, right? Because we are assuming things, it's not perfect, right? We are kind of making an estimate, so there must be limitations. So limitations for this probability type, right? The very first one is the experimental conditions may not essentially remain homogeneous and identical in the number of repetitions of the experiment. Second one would be the frequency m by n, the relative frequency, we call it the relative frequency m by n may not attain a unique value, may not attain a unique value, no matter however large maybe. What happens in this kind of probability is you cannot have always a unique value, right? Because it's a it's just a limit. So as my n goes higher and higher, the number of limit would not be, may not attain a unique value. That's what the limitations are, right? So with that said and done, right, let's look at where and how we can apply the statistical probability, right? We have already seen an example of classical probability theory. Let's look at an example wherein we apply statistical probability. All right, let's look at the following problem. What we given is a dice is thrown. Okay, we need to find the probability that the number is 5 greater than 4 and an odd number. Okay, I just have to add an odd number anyway. So if I look at a dice, first of all, then the number of outcomes, right, the total number of outcomes possible is 6. Let me use that here, solve it using differpan here. N is nothing but 6, right? Total number of outcomes is 6. Now, when a dice is thrown, how many times can we get 5, right? What are the possibilities to get number 5? Only one, right? So in the first case, what am I doing, man? Okay. In the first case, right, what happens is m is just 1. Therefore, if I name this as event A, B, and C. Right? So you got to write down let A be the event of getting 5. Right. Probability of event A, you can write down that probability of getting 5. Let A be the event of getting 5. Then probability of A would be equal to m upon n, which is nothing but 1 over 6. Similarly, let B be the event of getting a number greater than 4. Right? Then a number which are greater than 4 right, in this set would be 5 and 6. Right? So what I get in that case is m is 2. Therefore, probability of B would be nothing but m over n. In this case, this will be 2 over 6, which is 1 by 3. The third case, the third example, my m is an odd number. So what are the odd numbers between 1 and 6? 1 is odd, 2 is even, 3 is odd, 4 is even, 5 is odd, and 6 is even. So total number of outcomes 6. So therefore, probability of C is nothing but m over n, which is nothing but 3 over 6, which is half. So this is some simple problem. Let's look at a bit. We have a pack of cards, and what I'm doing is I'm removing two cards. What I'm going to do is I'm going to find the probability that both are black. Okay, then both are key, and one key and one. So before we proceed, we need to look at certain things when it comes to pack of cards. Uh, there'll be a lot of problems with respect to pack of cards and choosing something and so on. Right? This is a bit of higher probability theory. It's not as higher as that, but there are little bit of which are involved. So let's look at that. So when it comes to pack of cards, everybody must have known that there are 52 cards, right, in a deck. Out of which 26 are black, right, and 26 are red. Out of these 26 black, there are two kind of um, what I can say. Again, it's divided into uh, call that as uh, yeah. Black have two suits, namely spade and spade and club. This two suits. Again, each color has two suits. One is spade, there is club in black, and then in the red we have heart and diamond. Okay. Then each of these four, there are three face cards. Each suit has three face cards. So that's king, queen, and jack. Altogether, altogether, there would be 12 face cards, right? Because each will have three, and there are four suits. So together, there will be 12 face cards in a pack of, right? And each suit has one ace, right? And ace is supposed to be the biggest card, the strongest card when we play card game, right? So there'll be four aces in a pack, 12 face cards, right? Three face cards in a suit. So this is the thing about card, right? With this understanding, let's look at the problem. First of all, you know how do I choose something, right? How can I choose? If I can choose given object from n object in NCR, that is n factorial upon n minus r factorial into r factorial. You need to remember, kind of, right? So what happens is I have 52 cards and I'm choosing cards from 52 cards. So in how many ways I can do that? So each time I take two cards from 52 cards, right? How many such pairs I would get? If I want to calculate that, then that means I want to calculate what is going to be my n, right? Let's write that down first. Two cards can be chosen from a pack of 52 cards in 52C2 ways. Therefore, my n becomes 52C2, which is nothing but 52 factorial, right, upon 2 factorial in 52 minus 2, that is 50 factorial. If a little bit of combination ideas, what I can do is I can write it as 52 into 51 multiplied by 50 factorial and keep it as 50 factorial into 2 factorial. But 2 factorial is nothing but 2. What happens is this gets cancelled with this. What is left is 51. I can cancel this 2 with this 52. That gives me 26, right? So 51 into 26, right? And if I use a calculation and to calculate 56 multiplied by 50, sorry, 51 multiplied by 26 rather, I would get 1326. These are the total number of outcomes. But you don't have to worry about that because we're gonna cancel it anyway. So we're not just have calculated this for your kind of reference. Now let us look at the first option. Right? Let A be the event of choosing cards such that both are. Now there are altogether 26 cards which are black, right? In how many ways I can choose two black cards from 22 black cards? Obviously, this is same as choosing R item from n given item. Therefore, two cards can be chosen from a pack from two black cards. Black cards can be chosen from 26 black cards in 26C2. Therefore, my M becomes 26C. Right? So, what is the probability? Therefore, probability of A would be nothing but N over, which is nothing but 26C2 over 52C2, right? Now, this would be 26 factorial upon 24 factorial into 2 factorial over, this would be 52 factorial over 50 factorial into 2 factorial. So this 2 factorial get cancelled. If I use the about trick, this is just 26 into 25 over 52 into 51. Right? I hope you know what I've done. I've written this as this is 26 into 25 into 24 factorial, and then you cancel this 24 factorial with this 2 factorial gets cancelled with this 50 similarly will get cancelled with this. So 26 I can cancel with this. So what I get is 25 on top over this would be I can correctly calculate this. This would be 25 over 102. And if I look at into decimal, 25 over 102 give me something of the form 20.24, right? 0.25. 25% of chances that I would pick up a black. Both the cards would be black. Okay. So the first question was comparatively easy. Let's look at the second question. Second question is bit of a problem. Both are spades. Well, this is also not that difficult, but let's check out. I hope you're getting what I'm trying to do. If you have not understood, you can just write it down to me anytime. So let's look at the second part. Okay, what I want to do is I want to choose both are spades, right? So first of all, there are 13 spade, right? Therefore, two spade cards can be chosen from 13 spade cards in 13C2, right? Therefore, my M here becomes 13C. Therefore, let B be the probability of choosing uh, what to spade. Therefore, what happens to probability of B? Probability of B becomes 20, sorry, that would be 13C2 over 26. 52, right? Pardon. 52, right? 52C2. This is nothing but 13 factorial over 11 factorial into 2 factorial over 52 factorial over 50 factorial into 2 factorial. This is gets cancelled. Will be 13 into 12 upon 52 into 51. Then this 4, right? If I 3, so I get 3 by 51, right? 51 can be cancelled out, right? So what I get is um, 1 by 17, which comes out to be something around uh, 0.06. Yeah. Okay. I taken this as second. Okay, no worries, no worries. This would be second. Let me make this as 3. No problem. I didn't realize. Then if I can just you have copied the question. I presume that you have copied the question, and we are good to without even looking at the question. So the third one is both are kings. So third one is let use some different pen so that you don't get confused. Use green one. Let C be the probability that both the cards are kings, right? Now we need to remember there are 4 kings. right? So total number of kings are 4. How many ways I can choose? Therefore, 2 kings can be chosen from 4 kings in 4C2 ways, right? That's my M. Therefore, probability of C becomes 4C2 over 52C2. This would be 4 factorial upon 2 factorial into 2 factorial over 52 factorial over 50 factorial into 2 factorial. This gets cancelled. This will be 4 into 3. This would be 52 into 51, right? This comes out to be how much? 17. This comes out to be 13. So this is 1 over the product of both. This comes out to be 1 divided by 13 comes out to be this, and then again divided by 17. 0.004. 0.004. Let's check out. I do really don't know. I sometimes do mistakes. So we have this as 0.005, right? Let's look at the final question. This that is 1 king and 1 queen, right? Well, uh, first of all, we need to realize that we have 4 kings and 4 queens, right? Note that there are 4 kings and 4 queens in a pack of 52 cards. Right? One would be spade, one would be club, one would be diamond, one would be heart. So I can choose 1 king out of these 4 in 4 ways, right? I can either choose spade king or heart king and so on. Therefore, 1 king can be chosen in 4C1 ways. Similarly, 1 queen can be chosen in 4C1 ways as well, right? Therefore, so if I can choose 4C1 ways, 1 king in 4C1 ways, and also I can choose uh, 1 queen in 4C1 ways, right? That means 4 ways I can choose 1 king and 4 ways I can choose 1 queen. Then 1 king and 1 queen, right, together can be chosen into 4. I mean, can be chosen in 4 into 4, right? And right, that means I can choose them in 4 into 4 ways, right? Therefore, I have already written that. Sorry. Therefore, 1 king and 1 queen can be chosen in 4C1 into 4C1. Therefore, my M becomes 4C1 into 4C1 in this case. Therefore, probability, let me name this as let, can write this here somewhere. I'll write it here. Let D be the probability of choosing 1 king and 1 queen. Therefore, probability of D becomes 4C1 multiplied by 4C1, right, upon the total, that is 52C2, right? And if I do a little bit of calculations here, what happens is this becomes 4 into 4 over um, what this becomes is this is 4 into 4, and this would be 52. This is 4. 4C1 is 4. This is 4 into 4. This is 52 into
51 upon 50, so this becomes upon 2 factorial, so this cancels out, so this is 16 over this cancels out and becomes 26 into 51, but then I can cancel this out and all of those things if I do, right, and divide whatever the resultant I get, right, then I would get the number to be equal to um, 0.012. You can check that out. That's the probability of the event, right?